Okay guys, so this is spectroscopy part 2. This is the more longer style questions. You could call it the combined techniques question. So we're going to be dealing with infrared mass spec as well as proton NMR. And in an exam you could even get carbon NMR as well. But I think that's fairly easy. This is the harder stuff. I've also popped up the empirical formula. Quite often you'll be told that too. So what we're going to be doing is combining all of this data to figure out the structure of the molecule. And it's a fairly common question. It's also a very, very high mark question. If this comes up, it can be anything, up to 10 points or even more, which is pretty much a grade in your exam. So really important we know how to do this. It'll usually be the last question in the exam and it takes quite a while to do. So, if this does come up, there'll be maybe 2 marks for the final answer, your actual structure. The rest of the marks will be for showing your working. So imagine you're like a lawyer in a courtroom. You're trying to prove why you know that this is the right answer. It's not just about figuring out the answer, it's showing how you got there. That's really what it's all about. So it doesn't matter too much which way you start, so you can do it in kind of any order, but I think this is a good way to do it. I always start off with my IR data and we use that to figure out which bonds your molecule has and from that the functional group. So let's have a look what we've got. We have OH bond and that's round about 3,100. That's our first mark. You could possibly say we've got a CO bond around about 1,300, but because it's in the fingerprint region, it often gets obscured. So you'll never get or lose a mark for talking about that. There's only 2 bonds you really need to look for, your OH bond and your COO bond at around about 1,750. Now, we have an OH bond, we do not have a COO bond at around about 1,750. And you've got to put those wave numbers in brackets afterwards to show what bond it is you're talking about. Like, let's say examiner you know where this bond should come up. So we have an OH, we do not have a COO. Because we don't have a COO bond, it can't be a carboxylic acid, so it must be an alcohol. Or you could say the functional group is an alcohol, because the only thing that has an OH bond but does not have a COO bond is an alcohol. If we had an OH and a COO bond, then we could say it must be a carboxylic acid. So that's our first bit there. We know we have an alcohol. Let's have a look at my mass spec data next. I think that is logical to do this next, or certainly this molecular ion peak. So the molecular ion peak is the peak furthest to the right, not necessarily the tallest peak, just the one furthest to the right, and whatever your M over Z value is for your molecular ion, that is the mass of your molecule. M over Z is just mass over charge, but the charge is almost always +1, and a number divided by +1 is just the number. So whatever your mass furthest to the right is, that's the mass of your molecule. Now, if I just wrote mass equals 76, or MR equals 76, you wouldn't get a mark, because you're not showing your working. You're not explaining how you got there. So you need to say, because the molecular ion peak has an M over Z of 76, I therefore know the MR is 76. So you're explaining yourself. You're this lawyer, you're explaining your reasoning. And that would be another mark there. So I know the MR is 76. I also know my empirical formula is C3H8O2. Now, if I add up the mass of my empirical formula, that will equal 76. So I know my molecular formula has the same mass as my empirical formula. I therefore know my molecular formula must be my empirical formula. So therefore and don't just write the formula down. Don't just write therefore C3H8O2, because what is that you're talking about? Is that what you had for breakfast this morning? Is that what your name is? No, that's the molecular formula. So you need to write that. Therefore molecular formula equals C3H8O2. if I found out my molecular formula had twice the mass of the empirical formula, all I would do is double my empirical formula, that's annoying, double my empirical formula to get my molecular formula. So let's say my MR was 132. All I would say is my molecular formula is C6H16O4. Okay, so you just double it. Apologies about the noise, that's really annoying. So that's another mark there for saying my molecular formula. We then need to do a little table. We need to do chemical shift. We need to do, well, it doesn't matter which way you do it, but splitting. And integration trace. Sometimes integration trace is called relative peak area. So we've got 3 peaks. We've got a chemical shift of round about 1, chemical shift of round about 4, and then round about 4.5-ish. What splitting do we have? Well, we have, for 1, we have a multiplet. So, what does that tell us about the number of adjacent hydrogens? Well, if you watched my previous video, you'll know that to have a multiplet, we must have 4 or more adjacent hydrogens. So, 4 plus adjacent hydrogens. For my peak at 4, I have a triplet. So I know I must have 2 adjacent hydrogens. And you can't just do this in your head. You have to write it down or you won't get the marks. And for 4.5, I have a singlet, so I have 0 adjacent hydrogens. Okay. With 0 adjacent hydrogens, also, if it's an OH hydrogen, remember that will never get split. So 0 adjacent hydrogens, or it's an OH hydrogen. Relative peak area, I've just wrote that above. Sometimes it'll be in a table. We've just got 2, 4, and 2, and that just tells us the number of hydrogens in that environment. So I have 2 H's in the environment, 4 H's in that environment, and 2 H's in that environment. So that's kind of the easiest bit. That's putting all of the data, that's getting all the data down. What we need to do now is pop it all together to get our final answer. And this is a little bit of trial and error. You really just have to write a structure down which fits the molecular formula and then see if it fits this data here. So I'm just going to have to rub some stuff out to make a bit of space. Just rub the stuff at the top out. So I know it's an alcohol. But I've got 2 oxygens, so that means I must have 2 alcohol functional groups, so it'll be a diol. So let's have a look and see if some stuff fits. Let's do this. Well, how many different hydrogen environments would that give? We've got 1 hydrogen environment here, 1 here, 1 here, and 1 there, because they're in identical environments. That would give me 4 environments. Straight away I know that doesn't fit, because I've only got 3. So, trial and error, let's try shifting it around a little bit. So you see this process, I take a stab, it's an educated stab, but I still take a stab, and then I just try and see if it fits the data. If it does, perfect. If it doesn't, try again. So let's try this one. Okay, how many environments do we have now? We've got 1 here, 1 here, 1 there, 1 there, and 1 there. So 1, 2, 3, 4, 5 environments. Again, it doesn't fit. Let's try again. Just keep on having a stab, keep on changing it so it fits. Now, that was fairly easily identifiable as the wrong answer because I had a different amount of environments. If it did have 3 environments, I'd need to check my splitting and my relative peak areas to see if they was correct too. So let's try this one. Okay, I'm just going to get a pen. So, if you think you're onto a winner, if we have the right number of environments, then I do something called the string method. So let's see how many environments we have here. I'm just going to number these environments because it gets a bit complicated. So this hydrogen here and this one, these are in environment 1. These hydrogens here, because they're in identical environments, because we've got a symmetrical molecule, they'll be in environment 2, and these hydrogens here, they'll be in environment 3. So I have 3 environments. So my hydrogen's in environment 1. Let's have a look. Well, it's an OH, so it can't get split, so it'll be a singlet. And because there's 2 of them, there'll be a relative peak area of 2. I just realised actually the relative peak area will actually be 1 to 2 to 1, not 2 to 4 to 2, because it's always the simplest ratio. So apologies about that. It doesn't make much difference to how you'd answer the question, but it should be 1 to 2 to 1. But let's ignore that. So a singlet with a relative peak area of 2, I have a singlet with a relative peak area of 2. So far so good. For my environment 2, I have, well, remember OHs don't cause splitting and they don't get split, so I ignore that side. Let's look at the number of adjacent hydrogens on this side, that's 2. So that would n plus 1, 2 plus 1 is 3, that would get split into a triplet with a relative peak area of 1, 2, 3, 4, because there's 4 hydrogens in that environment. We have a triplet with a relative peak area of 4, bingo. And then finally, I have this one in the middle here. Well, that's got 1, 2, 3, 4 adjacent hydrogens, so that's going to be a multiplet, and that's going to have a relative peak area of 2, a multiplet, a relative peak area of 2. Let's also go back and check these chemical shifts are in the right place, and you'd use your yellow data sheet to do that. Let's have a look, yep, they're all in the right place for what they should be, so that fits the data. I can say this must be my answer. But until you go through and check it with this string method, just the splitting in the relative peak area and where the peaks are, you won't know that. Okay, and that is how to do long style spectroscopy questions.